Gnanam paramam dheyam. Knowledge is supreme.
Okay, so we have seen that your energy must be greater than V global minimum. Otherwise, solution does not exist, right? How did I try to give you an indicative proof? If you try to find expectation value of P squared, this should be positive. But if E is less than V global minimum, what happens? You can show this to be proportional to E minus V of x, expectation value, using the time independent Schrodinger equation, and you can show that this is E will be less if I take, then this is negative, right? Everybody was with me? So therefore, this condition will not give any solution. Okay. So we need E to be always greater than V global minimum. Locally there could be a minimum, but it should not be the global minimum. Whatever it is, your energy value should be greater than the global minimum. Is that clear? What about the other thing which I said, which is 1D bound states are non-degenerate. How do you prove this? You take the time independent Schrodinger equation. Okay. So you can take the time independent Schrodinger, assume that psi 1 of x and psi 2 of x are solutions. Okay. Assume. And prove by contradiction. So if they are solutions, then d squared psi 1 by dx squared minus 2m over h cross squared v minus e, psi 1 is 0. It's bound state. So we need to take E to be less than V. Okay. Let's look at this constant barrier potentials. Take the energy to be less than the potential energy of the barrier. Similarly, you can write a similar equation for psi 2 equal to 0. Both are allowed solutions is what we are assuming, which means for E less than V, both have to satisfy the time independent Schrodinger equation. So multiply the first equation by psi 2. Similarly, multiply the second equation by psi 1, and then you try to subtract one from the other. What happens when you subtract? Which term cancels? The second term cancels. What you will be left with is, what will you be left with? Psi 2 d squared psi 1 by dx squared to be psi 1 d squared psi 2 by dx. This can be further simplified as d by dx of psi 2 d psi 1 by dx minus psi 1 d psi 2 by dx equal to 0. What does this tell us? The square bracket can be put to be some constant, right? You can put it to be a constant. Psi 2 d psi 1 by dx minus psi 1 d psi 2 by dx is a constant. Okay, it's a function of x and it should be valid at all x. For x tending to plus or minus infinity, we are looking at a bound state solution where it should be exponentially damping. You expect, so what do you want? X tending to plus or minus infinity, what happens? Wave function itself will be 0, which means this constant, it's a constant, it should be valid even at x tending to plus or minus infinity. So for bound state, we can definitely put it to be 0. We can't do this for a scattering state because it will be oscillatory solution with a box normalization. As I said, if you had a solution for an oscillatory state as e to the ix, this is oscillatory solution. We do a box normalization putting a root L, and then after we do all the expectation value, we put L tending to infinity and nothing happens. Everything is fine. So these are all not the states we are considering for bound states. Bound states are the ones where the wave function vanishes. So these are scattering states. This is not what we are looking at in this specific proof. We want to look at bound states which vanishes at plus or minus infinity, and we are assuming that it is degenerate, and we are getting a condition like this. So can we further simplify this condition? Since this is 0, this first term is equal to the second term. Is that right? Excellent. So what does that tell us? Yes. So which means that you get psi 1 of x to be proportional to psi 2 of x. This k equal to 0 will automatically show that the two wave functions are not independent, they are proportional to each other, which means our starting point that it is degenerate is not valid. Degenerate means those two should be linearly independent, but we find that systematically substituting that they are degenerate and putting it into the Schrodinger equation and imposing that the wave function vanishes at plus or minus infinity forces k to be 0 for the bound state, and this condition will automatically show that psi 1 of x is proportional to psi 2 of x, which implies non-degenerate bound state. This is only applicable in one dimension, okay. So one dimensional problems, bound states are always non-degenerate. That is what you saw in the harmonic oscillator. One dimensional harmonic oscillator, you saw that all the solutions in the one dimensional particle in a box are all non-degenerate because of this proof. Okay. So the next thing is, once I have tried to take this assumption that the energy of the particle should be greater than the global minimum and the 1D bound states are always non-degenerate, we can look at symmetric potentials and prove that the solutions have to be either even solutions or odd solutions. So that's the next thing. So 1D bound state are non-degenerate if V of x equal to V of minus x, wave function solutions must be either odd functions. What is the odd function? Psi of x equal to minus psi of x minus x, or even functions, psi of x equal to plus psi of minus x. This is what we want to prove. Again, how do you prove this? Take the Schrodinger equation again. If you take the Schrodinger equation, Hamiltonian, which is a function of P and X, P operator and X operator to be very precise, we find that it is same as H of P with minus X operator, because V of X is same as V of minus X. We are looking at this class of potentials. One of the example is a harmonic oscillator, other example is a symmetric box which I indicated in the last lecture, and the third example is your double delta potential, which we are going to solve today, the remaining half of the lecture. Okay. So these are the three examples. Always try to, when you try to go over a proof, recall some example and keep it in that mind. Okay. Then you will never forget some of these statements. You will be able to correlate with an example and you will remember it properly. Okay. So that's why I am trying to give you those three simple examples so that you remember these things clearly. So what do we do usually when we write the Hamiltonian operating on psi of x, right? Hamiltonian will be in general a differential operator, will be time independent Schrodinger equation is some energy eigenvalue E times psi of x. So I could also write H of P minus x hat psi of minus x. I am just changing x to minus x, nothing more. Okay. It's allowed because if you write the explicit operator, it will be in the position representation. We find that the potential has this property, so we can write it in this fashion where the energy eigenvalue is independent. It doesn't care about which position you are looking. So what is this? So this equation is nothing but, because of this property, this is nothing but the same Hamiltonian operator on psi of minus x is E of psi of minus x. Okay, you all agree? So this equation, by using this property, I can try to write it as this. So what does this tell you? Psi of x is a solution, psi of minus x is also a solution. Okay, psi of x and psi of minus x are solutions of Schrodinger equation, time independent Schrodinger equation. But they are all, we are looking at bound state problems, which means psi of x and psi of minus x cannot be linearly independent, right? So psi of, they are solutions, but 1D bound state tells us that 1D non-degenerate bound states tells psi of x should be some epsilon times psi of minus x. They cannot be independent. X is a dummy variable. You can call x as minus x. If you do that, psi of minus x is epsilon times psi of plus x. So you can substitute twice. Instead of psi of x, you can substitute the above equation. It will become epsilon squared psi of minus x. So epsilon squared has to be 1. So which implies epsilon has to be plus or minus 1. So the epsilon is plus or minus 1. The plus 1 will correspond to is even psi of x, and the minus 1 will correspond to as odd. So I didn't do anything. I am only assuming that we are looking at bound state solutions for symmetric potentials. Looking at the time independent Schrodinger equation, you find both are allowed solution. Psi of x is an allowed solution, psi of minus x is an allowed solution, but 1D bound states have to be non-degenerate, which means they should be proportional, and then the proportionality constant epsilon squared has to satisfy a constraint which is 1. So the only solution possible are odd solutions and even solutions. So when we did this elaborate exercise of solving the time independent harmonic oscillator, we did not use these proofs, but the solutions which we found were either odd functions or even functions, right? And also the particle in a box, when you put it symmetric, your first ground state solution will become a cos function, right? For a symmetric, if you remember that if you took a minus L by 2 to plus L by 2 infinity potential, the ground state was proportional to cos pi x by L. Similarly, the first excited state is proportional to sine 2 pi x by L. This is what you will see in the particle in a symmetric box. And I also said that the ground state will always be symmetric. Okay. What we will do now is, we will take the double delta function potential. How many of you have already tried? Did any of you try the solution for the double delta? Okay. So we will just go over it so that you can recall. If there is any mistake in my typing, you should point it out. And basically you will find that because for the double delta you have the symmetric condition, the solutions can be assumed using these proofs, that you will have an odd solution or an even solution, and you will find that the even solution has a lower energy in comparison to the odd solution. Okay. So we will go over it, and both graphically as well as, yeah. So you could take it, but then when you take x2 minus x, epsilon squared is what you can do. E to the I pi is only minus 1. Okay, if you do that, it is e to the I 2 pi. That has to be set to 1. So you are stuck. Whatever you do, the nature knows when you do the Schrodinger equation, it picks out Hermite polynomials which are odd functions or even functions. It's very beautiful. One is just rigorous mathematics, the other one is by this kind of simple proofs that you can show that your symmetric potential should allow only for odd solutions or even solutions in one dimensions. No. So what he was saying is, let me put that sheet again. I don't know whether it will be visible. Let me see. I hope it will be. So what he was saying is that instead of this epsilon, which is to be plus or minus 1, why can't it be a complex phase factor? But what I was trying to tell him is that you need your epsilon squared to be 1. If you take a complex phase factor as e to the power of 2i phi, and that is not 1 for an arbitrary phi, unless phi is taken to be pi, the phase factor. If you take phi to be pi, then it is only plus or minus 1. Okay, so with this warm up, let's get to the double delta function potential. I thought, just to make it clear, rather than putting too many complicated equations, I thought let me put it on a PowerPoint or a PDF file. So just take a look at it, and then is this clear, the fonts and all? So I tried to draw it to the limit as possible. I am not very good at drawing, but I hope you understand that it is a double delta function potential. For graphically, just I have taken a to be plus 1, and so you have a delta function potential at a equal to plus 1 and a equal to minus 1, but you can keep this to be an arbitrary a. So I tried to plot in Mathematica. Unfortunately, one side it plots, the other side it doesn't plot, so I was struggling for some time, but then I drew it manually, this piece, but then I have not done a very good job. Okay, but you get the point. So I've just tried to give you a graphical potential. So this is the potential versus x, where you can see that there is a symmetry. It's not very obvious in the figure, but at least from this expression you can see that it's an attractive potential. If you take x2 minus x, this term goes into this term and this term goes into this term. Is that clear? So does this allow bound states? The first thing you have to see is what is the global minimum. Global minimum is negative infinity. So your energy can be less than the local minimum at plus or minus infinity. So you can have a E negative, and you do get bound states. Okay. So recall bound state condition, and E should be greater than global minimum. And also note that the potential is a symmetric potential. So I have already proved for you. that for symmetric potentials and 1D bound states, now we are looking at bound states, the wave function has to be non-degenerate and it should be either odd functions or even functions. We are going to use this property when we write the solution. Now we are not going to write blindly solutions, now we are going to incorporate this fact. Okay, so the bound state condition will be energy should be less than 0 because at plus or minus infinity the energy is, the potential is 0. So you can have an even solution. You can split this into a regime, region 1, region 2 and region 3. And region 2 you can have this cos hyperbolic, not a linear combination of e to the alpha x and b to the alpha x, because this should be a symmetric even function. And similarly for region 1 and region 3, mod x is greater than a, you will have a symmetric function. The same b will appear in region 1 and region 3. So you don't need to put a b e to the power of minus alpha x and c e to the power of minus alpha x. This is all I am trying to say. That's what you would have done. Now you can simplify it and say that the symmetric potential will allow this. Okay. Alpha, of course, you all know it will be, E is negative, so alpha is positive, and this is the definition of alpha. So what is the next thing? Wave function must be continuous at x and x equal to plus or minus a. Those are the two boundary regions, and you can put in that condition. Now very easily we can do this at plus a or minus a. Okay, so I have taken one of the regions. But you have this delta function potential requires that there is a definite derivative discontinuity. We have seen this. So substitute the definite derivative discontinuity and you will get an equation where it is plus epsilon the derivative at plus or minus a, and similarly the derivative at minus epsilon shift at plus or minus a boundary. Is that okay? So you can simplify this in this even solution which I have given. So you get a condition from the derivative discontinuity, an equation. What is our aim? Our aim is to determine energy for the bound state or alpha. Alpha is a function of that energy. Alpha is positive and energy is negative. So what next? You divide 1 by 2, right? Then you get a simplified form from which is it easy to determine alpha? You have done some similar problems in your assignment sheet where you don't really get a explicit analytic solution for alpha, right, from this expression, but you can start getting the trend. Take alpha in comparison to the width a, the position of the delta function, whether it's small, whether it's big, and we can get some kind of a trend. And then we could also go into trying to plot them in a graph and see whether there is a solution, and wherever is the solution you can pick out what is the energy.